Good afternoon, everyone. Welcome to the afternoon session. It's my pleasure to introduce our first speaker, Jakiw Pidstrigach. Sorry about this. And he is a postdoc researcher at the University of Oxford, and his research interests lie in the generative diffusion models, Markov chain Monte Carlo, stochastic analysis, and interacting particle systems. And he will be speaking about infinite dimensional diffusion models.
Thank you very much. Yes, so this is the title of my talk. It's joint work with my co-authors Yusuf Mazouk from MIT, Sebastian Reich from Potsdam, and Sven Wang, who's now in Berlin. Yeah, so a short overview. Also, as a caveat, this talk yesterday I timed it, it's going to be shorter than 1 hour. So in the end, I can maybe also actually say something a bit on memorization, which would be, I think, of big interest and also connected to the talk from today in the morning. Yes, but okay, now for infinite dimensional diffusion models, except all of you ask many interesting questions, then we will fill the hour with this. So first, the general introduction for diffusion models, as always. We have, or what is generative modeling in general, we have some samples from a measure, and our main goal is that we want to generate more samples from the same measure, and also do density estimation, although that's normally not so important in machine learning. And how we do this is by adding noise to the distribution and then reversing this process. And then there's always this image where we want as a goal to learn something where we can start in this very noisy, with a noisy sample, which is easy to generate, and then go to some clean sample from our measure, in this case, a picture of a dog. And we do this by, I mean, there are multiple frameworks. You can also formulate it completely in discrete time, but it's also very nice that you can actually formulate it very well with stochastic differential equations. And so how we do it is how the noising process is relatively easy. It's with an Ornstein-Uhlenbeck process. So we start in some distribution P0, and then we just run an Ornstein-Uhlenbeck process, of which we know that it will converge to a normal distribution relatively quickly. And let's denote the marginals, the time t marginals of this process by pt. And then if you pathwise reverse this process, so really look at this, and then you look how it goes backwards, then it satisfies a reverse SDE, as Annie has showed today in the morning, even in infinite dimensions. And these are mostly results from the 80s. And yeah, I mean, there's also, I mean, it's quite intuitive on the ODE level there, that you basically switch around the drift, which is what you also would do if you would run an ODE backwards. Then what's maybe a bit confusing is that here you've been adding noise, so you've been smoothing out the distribution, and here you're also adding noise, and so you're also smoothing out the distribution. But this term here kind of counteracts the addition of the noise, and even more push it, like it kind of counteracts it, like pushes the samples of the reverse SDE to high probability areas of XT. And the very nice thing about this is that if you now start the reverse SDE in the, like if you run the reverse SDE, because it will have the same time t marginals as XT, then you will get at the final time, the final distribution of the reverse SDE will be the same as the initial distribution of the forward SDE, which is your data distribution, so the thing that you want to sample. Therefore, this gives us a nice candidate of something that we would like to simulate. And if we could simulate it perfectly, then we would get samples from our data distribution. And of course, that's not so straightforward. So what are the problems with just simulating this SDE? Well, the first one is that we don't know the initial condition, PT, because we didn't know P0. P0 was given, like, was the initial distribution of X. So mu data, some unknown distribution. And PT is just some smoothed out version from it. So there is some information still there. We don't know that. And the same thing, the same PT appears here again in the drift. here, by abuse of notation, here I use it as a measure, and here I use the Lebesgue density with the same letter. This will play a role later. So how do we solve these two problems? The first one is because it's a forward SDE, we chose the Ornstein-Uhlenbeck process. We know it will converge to the standard normal distribution relatively quickly. We just say, okay, at time t, we've run it for long enough. We will just say this is normal already. And for the second part, we can actually approximate this here using a neural network. That's why it's called machine learning. And you have this loss. Here in the loss, actually, the PT itself appears still, but you can rewrite it so that you can actually train it by just having samples from x0 to xt. We will also see that later again. And here the image, which kind of tries to summarize it. So you start in some distribution mu data, which is your target distribution, which you would like to generate samples from. Then you run the forward SDE. Here, normally you would run it long enough that this looks very similar to a Gaussian, but to show that this is not necessarily the case, here I stopped it early enough that this doesn't really look like a Gaussian that much yet. Then if we could now start in this distribution and run it backwards with the perfect drift, we would get the perfect distribution, but that's not what we do. We switch to another distribution, which is a normal distribution, and then we run it backwards with an approximate drift that we have learned. So there are these two errors, and then you will land in a distribution, which hopefully is similar, but probably not the same to your original data generating distribution. And what I think is very impressive is that these algorithms are also able, so here you see the reverse SDE for a uniform distribution on the sphere to get like very like manifold kind of structures or concentrate all the math on also very low, like some substructures of the full space. Very well. Okay, now I'm going to do a quick excursion for Gaussian measures and infinite dimensions before I start to talk about the infinite dimensional diffusion model stuff, to also like to motivate the notation I have there and give some explanations on that. And the main reason here is that in this forward and reverse SDE, we have this term. So this is a Brownian motion. In Rn, you're just adding a standard Brownian motion. But even in Rn, you can think that you maybe want to change the covariance. And in infinite dimensions, in some sense, there's not even such a, I mean, one can argue about this, but it's more clear that you have to make a choice here. Which kind of Brownian motion are you adding? Which in finite dimension would correspond to choosing a covariance matrix, but people just say we use the identity, so normal Brownian motion. Okay, so why do we talk about this in infinite dimensions? So the first thing is that Gaussian measures with different covariances in infinite dimensions get singular very quickly. In finite dimensions, of course, you can also, by changing covariance a lot, get very different measures. But in infinite dimensions, all of this is more pronounced, and you like really get very different measures with different behavior quite quickly. And this holds also for this forward process. By changing the noising process, you can land in quite different areas of the space. Yeah, and this is the second point. And okay, let's quickly think about what a covariance is. To get the notation down, I want to introduce the Cameron-Martin space very quickly because I will be talking about that soon a lot. So in some sense, we want to choose the covariance of a Gaussian measure, and this is equivalent to choosing something called the Cameron-Martin space in infinite dimensions. And to motivate this in finite dimensions, if you have a Gaussian measure, which is non-degenerate, you can actually, it induces a scalar product, right? So if you have two vectors, you can just apply them to your Gaussian random variable and take the covariance of these two things. Then you will get some inner product structure. And actually the covariance matrix in finite dimensions is defined exactly by defining this inner product. And if we call this inner product U, or maybe Rn Rn with this inner product, we call the space U, then in U, the Gaussian measure would be a standard normal distribution. So equivalently to saying I'm defining an inner product like this, there should be a, Okay, there's a mistake here. So the inner product in U is defined with C to the -1. But basically, through getting a covariance matrix C, you can equivalently define some space with an inner product in which this Gaussian random variable would be IID, basically just standard normal. And this is like the main takeaway that I wanted to do here is that the choice of the covariance, also in finite dimensions, you can just see it as finding a covariance change under which you have a standard Gaussian. And that's a good way to think about in infinite dimensions, but some things that change in infinite dimensions. And this also gives you the reason why maybe we have more of a choice, because basically in infinite dimensions, we will have to choose one Hilbert space. And we say on this Hilbert space, we want it to be something like a standard Gaussian. But what's different in infinite dimensions is that this measure which we would get here, so the standard Gaussian on U would not be supported on U itself anymore, but only on a larger space. And one example, which is very easy to see, to check this, is that the norm of this thing, because now you check this would be an infinite vector and each coordinate is standard normally distributed. So if you look at this expectation value, it will be an infinite sum of ones. Basically, in RD, you would get just D here. In infinite dimensions, you get infinity, which does not mean that it could still be supported on U, but actually the infinite variance. So you now see that it has infinite variance. It could still be supported on U, but actually it's also not supported on U anymore. So you have this space on which it's standard normal. It will be supported on a larger space only. And again, back to the point that the Gaussian measures can get very singular to each other very quickly. I think one of the main examples which shows this is if you have a normal distribution with a covariance and then you multiply the covariance by any number which is not equal to 1, you get two singular measures. Okay, this is the image. You should keep in mind, I will also write down the notation for you in a second, but basically choosing this Gaussian measure in infinite dimensions or choosing the covariance in finite dimensions, it would be equivalent to choosing this space U. We will use this to choose which kind of Brownian motion we're adding. And you also normally, for many things, you might want to choose a larger space H on which the thing takes place, but this one is a bit more arbitrary. And yeah, and maybe also to, if you just want to think about it from a finite dimensional viewpoint or why does this matter, then much of this is actually the choice of the covariance matrix in the diffusion model. So, or basically putting a C in front of the Brownian motion, not noising with standard normal, but with some colored noise covariant noise. And one intuitive thing is, for example, if your distribution already looks close to some Gaussian or something, or you have some kind of covariance structure in your distribution, you might want to just have a better chance of very quickly converging with the forward STE to a normal distribution which has a similar structure than going in a completely different area of the space. And also just from a training perspective, maybe if you're adding like noise, which has a covariance structure, you're just going into a much smaller region of the space in some sense. And maybe you can actually gain something by not having to train the neural network in all of the space, but just in this smaller region. Okay, and now we can actually talk about infinite dimensional diffusion models. So yeah. Let's look at the problems that appear. I mean, I hinted a lot on one of them already a lot. In infinite dimensions with the normal diffusion model formulation. And the first one would be that which Wiener process are we choosing here as the noising process? In finite dimensions, this is what kind of covariance structure do we want for it? This is our problem one. And for now, we look at the reverse SDE. We have, of course, the same problem, but the reverse SDE. So let's say we will have the same choice here, basically. And also in the reverse SDE, changes to the normal formulations that you now get the C also in front of your drift. And the problem in the reverse SDE is that these were Lebesgue densities, right? So in finite dimensions, what we did, we had the Lebesgue densities PT at each time here, and we were taking some gradient of them. But in infinite dimensions, because you don't have a Lebesgue density, you also don't have a Lebesgue measure, you don't have Lebesgue densities. So it's not really clear how to make sense of this term. I mean, we saw one way today in the morning already, but I will show a bit of a different way, which works because we have a quite simple forward SDE here. And the problem 3 is, of course, I mean, in finite dimensions, we use the denoising score matching objective to approximate this term. What do we do in infinite dimensions? So can we still use this? Does anything change? And now we first come to the solution of the problem 2. This is, yeah, so basically what we use is that in finite dimensions, there's something which is called Tweedy's formula also. You can rewrite this term here, the drift or the score, as this conditional expectation. Maybe with a minus there. And this thing here carries over to infinite dimensions. So we can define the conditional expectation also in infinite dimensions. And this is what we do. So we just define S, the drift of our reverse SDE, as this conditional expectation in this simple case. And then we will try to work with this and see if we can still prove that the reverse SDE actually satisfies an SDE with this drift in a way that I will make precise soon. And the next thing is now, how do we approximate this? And we can still use the denoising score matching objective. And here, actually, in this formulation with the conditional expectation, the denoising score matching objective, I would say, becomes even more intuitive. Because you start with this conditional expectation, and we know that conditional expectations are minimizers, or expectations in general are minimizers of the L2 distance. So basically, this is the denoising score matching objective, where you say that if I want this thing, either I can just optimize my S theta to be equal to this thing, which would be nabla log PT, or I can actually just optimize a function which is allowed to depend on xt to be equal to the integrand of this thing, right? And then this is called the denoising score matching objective, where just optimizing for exactly this thing, which we don't know in closed form, is the score matching objective. And here, what we're doing here in this case is letting the neural network predict this is exactly actually equal to the noise of the forward process, right? So if you look at what this is doing, this is you can see that this will be the noise that is used to create xt from x0. So we're basically having the neural network predict the noise. You can also actually reformulate it, because you can, of course, say, you know, xt, right? So you can take this thing out and instead let the neural network predict x0. So basically predict the clean image. And these are also two different things that people...
Yeah, it's important here to understand the distinction between these two, right? Because formally, your first line is a function of x, of little x. The second line is not formally a function of little x. So perhaps you want to clarify.
Yeah, this should be little x here in this case. Thank you. So the xt in the last thing is little x. Yeah, but I think this is actually quite intuitive and actually makes the connection between the denoising score matching and score matching objective quite clear. And now in infinite dimensions, again, I mean, in finite dimensions, we just use the Rn norm here in the same way that we're just adding a standard Rn Brownian motion. And in infinite dimensions, again, we also could ask ourselves, which norm do we want to use here? In the same way that we're asking ourselves, which noising process are we using? So, and basically we have our algorithm now. I will now explain. So basically we say we want to run our reverse SDE with this drift which we are learning in the same way as before. So we can use the same objective to approximate it as before. And now we want to prove that this is a well-defined algorithm in infinite dimensions. And there are a few things that I will maybe fix now to keep the notation a bit clear. So the first thing is that we have the loss norm K. This is, the norm we're using in the training loss. Here's my high-tech thing, wait. Okay, then we have the Cameron-Martin space U, which is equivalent to the covariance of the Gaussian measure of the Brownian motion that we're adding in some sense. And we also have an embedding space H, which is larger, but that can kind of change depending on what we need. And lastly, we are given, well, let me write down embedding space. We are given mu data, or more, how we think about it is that we are giving the smoothness of mu data, of the typical samples of mu data. And now we want to show that the algorithm that we have this way is well defined. And what we do is first check the time reversal. So again, we pathwise reverse the forward STE, and we want to see, does it satisfy a stochastic differential equation or stochastic integral equation with the drift S. Then, if this is true, then we have this reverse STE, and this is a candidate to be able maybe to simulate it to get samples from mu data. Then the second thing, if we're simulating an STE, we would like it to have unique solutions, or in our case, at least unique in law, to get actually the right samples. If there are multiple solutions to it, then simulating it, we are not so sure what we get. Then we want to somehow approximate the drift that we're using in the reverse STE. And for that, we have to check when is this loss, this denoising score matching loss that we have in infinite dimensions well defined. And lastly, if we do errors in the drift, if we do errors in the initial condition of the reverse STE, things like discretization errors by using Euler-Maruyama, how do these propagate to the sample quality? So these are Wasserstein bounds. Okay, so it's a bit of another order than before. The first thing we check is the loss, and we can actually see that the denoising score matching objective, or basically the thing that we are regressing again, has finite variance if one of the following conditions holds. And we wanted to have finite, so why do we check for finite variance? Because we're using here that the optimizer is the L2 minimizer of this thing, but therefore the thing that we're regressing against should be in L2 itself. Also, in another way, you can also see that you want finite variance of the objective, because in reality, what you're doing is taking mini batches of this expectation value and then taking gradients of it. And if this has infinite variance, even if you're already at the optimizer, this is not something that you want for your algorithm. And lastly, actually, the finite variance is also the same condition if you want to see in which cases is score matching or denoising score matching equivalent in finite dimensions, or also in infinite dimensions. Then you also want this, random variable basically to have finite variance. So yeah, the denoising score matching means basically the thing in the expectation value has finite variance. And this holds if one of these conditions holds, and there you have two different ones. The first one being that the Cameron-Martin norm U in the first one, we say that mu data, so the data distribution is actually in the, so basically we have this space U here, and we say that mu data is supported in this U in a quite nice way, and which means that because we're adding noise with Cameron-Martin space U, and normally that means that we're adding noise which is itself not in U but in a rougher space. So we're adding more rough noise than mu data itself is in some sense. This would be one, but then we can actually use the Cameron-Martin norm in the training loss, or any weaker norm.
Stupid question. K was a loss norm.
Yes.
Supported on K. What do you mean?
Um,
The norm is some norm is finite or
Hey, yeah, I mean, I'm formulating a bit loosely. Loss norm in the sense of it also induces a Hilbert space. So K is the Hilbert space. Sometimes I mean the norm, sometimes I mean the Hilbert space. But basically, yeah, so the second condition, thank you. The second condition is that mu data and N0C are both supported on K, which means, so in the first case, I say that mu data is here and I'm adding rougher noise, but I can use a quite strong norm in the loss. And in the second case, I don't say anything about this, but the loss norm that we're using is much weaker. Okay, now that we have a way to approximate the drift, maybe let's check if the reverse SDE satisfies this. And indeed it does. So basically, if we have the pairwise reversal of the forward SDE, and I think this is also, I mean, I would like to discuss it in which way this carries over, but I think this is also a special case because we have quite a simple forward SDE here, not a very complicated object. So we can actually write the reverse SDE with this as a drift. And because there is a bit of a question, I mean, the conditional expectation is defined almost surely, but you can here choose a version which will be almost surely continuous in T. So it will be actually a continuous drift along the path. And the proof idea is by doing finite dimensional approximations, basically. So basically you have all these xt_d, xt1, which are approximations in the spectral coordinates of C. So C gives you an eigenbasis in which you can discretize stuff. And then these are all forward, just like Ornstein-Uhlenbeck processes. Plus, and then for each of them, you can use the finite dimensional theory to get a reverse SDE, of which you know the form. And here you know that these reverse SDEs will have exactly the form that we're saying, because they will have this nabla log. And we know in finite dimensions, we can rewrite the nabla log as this conditional expectation. And then you have a Brownian motion here. But what's important is that these Brownian motions will change from dimension to dimension. They're always like you will have another Brownian motion for each coordinate, and also in the Dief, at the Dief place, if you use the Brownian motion like for the Dief discretization and then project it down to the first few coordinates, this won't be the same Brownian motion that you got when reversing the lower discretization first. But what's nice is that this is a martingale in the dimension D or something similar to it. And the same holds here. You also have martingale properties for this because all of these are conditional expectations seen in the right thing. And then also this is a martingale in the time direction. And therefore you get the result. And you actually get, yeah, okay, no, this is later. Yeah, so these are the main points. And then we want to check that the reverse SDE is unique. So what we do is that we prove it in two special cases. In the first one, we say that mu data is contained in a Cameron-Martin ball of some radius. So it's basically, again, we're adding rougher noise. We again say mu data like this kind of case, which is in some sense, in this, because these kind of like resemble slightly also the cases for the log. And I think like the intuition here is in this case, mu data is contained in the Cameron-Martin ball of the noise. So you're adding much rougher noise, but mu data can look as what you want. It can have some submanifold structure, which is maybe a realistic assumption for images. And in the second case, we say that mu data already looks relatively close to a Gaussian measure. And in that case, you would not want to be, I mean, intuitively, at least, you don't want to pick much rougher noise. And if your thing already looks like a Gaussian measure and add much rougher noise, but you maybe just want to use the forward process, which will go exactly to this normal distribution. And in this case, you can also prove uniqueness. And here we have to go back to rewriting the reverse SDEs again with densities, but we use densities with respect to Gaussian measures, which differ from case by case. And then we prove some kind of Lipschitzness of these densities. And then we do Grönwald for uniqueness. And lastly, this is the Wasserstein bound. So now, because what we want to see is basically if we have an error in the loss and the numerics and the initial condition, how does this propagate to the sample property? And here, this is basically your training error. If you would say the training error is against the true data distribution, not against the training data, but you have this. The numerical error can be upper bounded by this thing here, where we again use that the drift that we're using is a martingale in T. And it's actually quite similar. I haven't read the paper yet, but I mean, this is relatively new work from Dormu with the finite Fisher information is all that you need. And I mean, this is a similar condition, so I need to check that. And then the error you make in the initial condition by not starting in the real thing, but somewhere else. Yeah. And because we have strong uniqueness, so how we prove this is because we have strong uniqueness of the SDE, we can solve them with respect to the same Brownian motion. We can do a synchronous coupling, and then we use the martingale properties of the drift to get this form of the numerical error. Okay, and lastly, so basically, if you now just want to apply the stuff.
May I ask you something?
Yeah.
How do you find how do you prove like the result for Wasserstein?
Wasserstein?
Yes.
So I mean, this is.
For example, what you cited, like Alan does in Andrews does like in KL, not Wasserstein, and that's quite a difference in them.
Yeah, and Alan also does not have this, right? I mean, this is like this is not a state of the art. This is more seeing that you can do a proof without dimension dependence. But what Alain has is also, he has that you need finite Fisher information, right? Which basically means nabla log P0 squared expectation is finite, I think.
Yeah, but it's a KL result, which is very different from Jones. So like I'm interested in understand how you prove this.
How I prove this?
Yes.
I mean, with KL, you normally just do the Gerzenov stuff, and then you get, I'm not exactly sure what they did, but here, so Wasserstein, what you do is you say, I have the two SDEs, you say, and therefore you need the strong uniqueness. I can solve them with respect to the same Brownian motion. Then, and then you can take the difference of the two paths, and the Brownian motion term cancels out. So this is like the most straightforward, easy way to do it, kind of. And then you just have an ODE for the difference of the two, and you see how it decreases.
Okay.
So with everything.
Contraction.
Hmm?
You need some contraction for this degree.
No, this is.
This is
This is not like if you would really do a nice thing, then you would try to get rid of this here, because yeah. But I mean, if this would have been included in the paper, it would have been even longer. So yeah, this is more like how something this can be done dimension free, and you can probably use some of the newer results to maybe also get rid of this stuff. I mean, I don't know in Wasserstein though. Like, I mean, most of them are in KL, and in KL in infinite dimensions, it's of course a bit, you quickly get like that the initial conditions will not be absolute continuous to each other, and then you have problems already. Okay, and now this is thank you for the basically for the applier. So we compiled the Wasserstein bounds and the conditions that we had on the different things to two different settings, which theory predicts that should work kind of well. And the first one is that you match the support of your, or like the smoothness maybe of your data distribution to the loss norm. And then you use this as a Cameron-Martin norm kind of. So you're adding rougher noise than your data in some sense. You're saying your data is in the Cameron-Martin norm, in Cameron-Martin space. And the other case is that you actually, so if this already looks like a Gaussian kind of, so this is all a bit hand wavy, then you're trying to actually match the smoothness of the samples of your measure to the smoothness of the samples of the Gaussian measure. So you match it to H, not to the Cameron-Martin norm, and you have a smaller one, and then you use the same norm again for in the training loss. So basically, this is the question, like which loss should be used, which covariance should be used, and what is predicted by our theory. And I think what's important to say is, so the standard implementation of diffusion models, there we just add a Brownian motion, right? And we increase the resolution of the images or the dimension of the space as we want, but we're still adding Brownian motion, so independent noise in each pixel. And you can see that this will converge to basically something that people often call white noise. And it corresponds to choosing a Cameron-Martin space L2. And also they use the same training loss, actually. So they use the training norm equal to the Cameron-Martin norm of their loss in some sense in the limit. But what's important to note is that this is a setting that's treatable, right? Because you don't have to add smoother noise to make it trace class or something in infinite dimensions. You can do this. You just have to view the whole thing in another Hilbert space. And it actually, in our case, we would say that this kind of adheres the choice to our option 1. So what we would suggest here, because if you say that the question is, of course, where do images lie? How smooth are images? But if you say that images are approximately L2, then it would make sense to be adding L2, using L2 as a Cameron-Martin space and as a loss. So this is basically what our theory says here. Of course, if you say maybe images are a bit smoother than L2 actually, then this would say you could maybe improve a bit by adding a bit smoother noise. But the question is also how much smoother than L2 are they? Because they are probably not continuous. You have the corners in the images. So probably actually the L2 noise is kind of a good first thing, or like a good default choice. But in the case that we have much smoother measures, then our theory says that we should pick other noising processes and other loss norms. And now for the end, some nice plots. We have here one toy example where we have something that's like a manifold. Basically, we generated Gaussian samples in some Sobolev space, and then we projected it to the unit sphere in another Sobolev space, which is higher. This is how the heat map of the distribution looks, and this is how the samples should look. Then we train diffusion models. And this is basically the white noise, where we're adding white noise. So we're using U equal to K equal to L2, the default choice, like standard Brownian motion, L2 as a loss. And this is what our first, like we had these two options, and this is the first option, basically what it would suggest that we do. And you see that both get the heat maps kind of right. You see some more noise here, and you see it more in the samples, but I'll say something about the sample smoothness in a second. So these are the heat maps, but I would say the heat maps are both kind of fine, so they get the marginals and stuff right. But now if you check the sample smoothness, then you see that the infinite dimensional one, which follows the guidelines with the smoothness, will produce samples from the right smoothness throughout, whereas the white noise one is kind of unstable. In the beginning, it nearly learns the right smoothness for most of the samples, but then actually is kind of unstable in that regard and loses it again. And then the second thing where we have inverse problems. So we did a Bayesian inverse problem with some to have this second case where our measure looks kind of like a Gaussian. So we simulate volatilities, and then we simulate SDEs with that volatility. We train the diffusion model, and we want then in the end to predict the volatility of some discrete SDE observations. And then as a test, so we train this with many paired observations. As a test, we inputted one specific observation in the end, for which we generated a true posterior with Hilbert space HMC to get a comparison of this is how it should look like. This is how the true posterior should look like, heat map and sample. And these are our algorithms. Again, the white noise one. And you see here it actually performs a bit worse also in the marginals. but this is also kind of to be expected because the white noise one doesn't know anything about the Gaussian prior measure we're having. We didn't tell it anything. What it needs to do is it needs to learn everything, the measure, the conditionals, whatever. And the second one, we gave it exactly the right Gaussian measure in the noising process. So in some sense, it has all the information on the prior, and it can use that and basically more like hand wavy needs to learn just the conditioning in some sense. And for the samples, we have a similar image as before. The white noise actually gets it right in the beginning and the end. In between, it's unstable for the sample smoothness, whereas the other one has the right sample smoothness all throughout. But I mean, as a caveat, these white noise diffusion models, they work quite well. And if you retrain it a few times and check a bit, you can get them to produce the right smoothness also for relatively smooth things. It's possible, but in general, I would say what we observed is that it's less stable in this regard, like these things happen. Yeah, that's it. Yeah, I can say something quick about memorization, but it will be a bit different. So, I mean, I don't know in which order.
Yes. Let's see first the
Is there
questions and then yes, then we move to the next part.
Do we have any questions?
I'm interested in this splitting into coordinates, which is how you get the limit to the infinite dimensions. Is that very technically intricate? It seems quite surprising to me that you can recover the density functions like kind of component wise. Is that like is that standard or is that like canonical?
Yeah, I mean, it's standard for infinite dimensional stuff. You discretize and then you hope it's independent of the dimension.
Yeah.
But yeah, so it is a standard like this kind of discretization. If you have the covariance operator C, you choose the eigenfunctions, you discretize in this way because the forward thing actually will decouple very nicely in this coordinates. So it is kind of a default thing, I would say.
Oh, I guess that's true because the forward dynamics are basically independent. Are they completely independent of
Yes,
each other?
in this
right?
coordinate system, these are actually independent SDEs in each. Yeah.
And does that mean that
so not fully, so D means D-dimensional, right? So it has the first D coordinates.
yeah.
But basically each coordinate is independent, yeah.
And then the score functions are they also independent? Then they wouldn't be independent.
No, they are not independent.
Yeah.
Because they can use information from the other coordinate
Yeah.
to, yeah.
Okay. Thank you. Yeah.
But, that's actually one of the, I mean, I don't know, in Vollmer's paper, he says this is one of the reasons why sometimes the reverse SD doesn't exist in infinite dimensions because of, or why it's not an SDE anymore, because you have all this information going through.
So you can have cases where the forward STE is perfectly well defined, but the backwards process doesn't exist.
Yeah.
Okay.
But not here, not for this simple
Yeah,
forward
I see.
SDE.
Thank you.
Any other questions?
Okay, I have a naive question. What about some kind of nearest neighbor interaction, if that makes sense? I guess in a pixel environment, it might make sense. Would that mean the diffusion matrix, which would not be identity, but some kind of taking into account the nearest neighbors?
Yeah, I mean, one could try to learn, for example, just take your image data set and learn the empirical covariance matrix or something like this, right? Is this what then you would get the nearest neighbor relationships in there, kind of? Yeah, I mean, it's actually, I ask myself the question, like, if you have the empirical covariance of most of these image data sets, how do they look like actually? Like, how far would this covariance be from something that you could see as kind of white noise? Or how much structure do you have actually? Because you have all the neighboring things which are the same, but then you have the jumps, right? In some sense also, it seems like Gaussians are not the right thing, the kind of noise to model that, but it works quite well. And I mean, the white noise thing basically just means each neighbor is independent from each other. So you for sure allow for like this is all very hand wavy now for jumps, but yeah. I mean, the question is basically, could you go a bit smoother, which would then say you have some neighboring relationship between the pixels? So could you add a bit of smoother noise than white noise maybe, and improve the stuff? But
And I have another live question. At the very starting point for your infinite dimensional setting, you dealt with an Ornstein-Uhlenbeck process, not Ornstein-Uhlenbeck-like.
Mhm.
A strict Ornstein-Uhlenbeck,
Yeah,
I
yeah.
dare say. Can it be extended to something slightly more Ornstein-Uhlenbeck-like?
I mean, the thing is, you can write down the reverse STE, I mean, as you know, for everything. But
Does
what
that
you
make
really,
sense on a practical basis?
Yeah,
My
so-
question.
yeah, so basically two properties you really want for diffusion models is the first one that you can approximate the distribution at time t.
Mhm.
Ornstein-Uhlenbeck has this, it goes to normal. And the other one is that during training, what you normally do is you sample x0, then you sample a random xt, and then you try to predict x0 from xt again. And for this, you would rather not want to run the full SDE, but you would like to be able to do this in closed form. So I would say diffusion models would work relatively well with, and like, so basically if you have a linear SDE, you can write down the transition kernels at time t, and then you can do the training process cheaply. I would say as soon as you go nonlinear, things get way more expensive.
You mean linear SDE, that the coefficient should not depend upon t? That's your the drift coefficient should not be a function of t multiplied by xt. That's
It should.
because for me linear and globe, I mean some function depending upon t, but of course it's not strictly speaking linear.
It should be a linear function of xt. So
Yeah, that's for
L
sure.
can depend on t.
Yeah, right.
But basically, any case where you can just write down ODEs for mean and covariance of the transition kernel, and then in the end, just use that. This is what you want.
Yeah, that's what I meant.
Yeah.
So it can be slightly more general, I suppose.
Yeah, for sure.
But I don't know whether it's interesting or not, because as I said this morning, I have no expert at all about artificial intelligence.
yeah, it's I mean, they call, like, in the diffusion model literature, the Ornstein-Uhlenbeck process is called the variance preserving SDE because
okay,
and
that-
the Brownian motion variance explode. I think it's quite ad hoc. Like, it's just one of, first I think they were just adding noise, which would be Brownian motion, and then kind of this idea with the Ornstein-Uhlenbeck came. If
Mhm.
there's another simple linear SDE which converges very quickly to something and you can solve it, then
That's
for sure you can use it. But the question, yeah.
Okay, thank you.
Thank you.
Any more questions?
No, good.
Then let's thank Jakiw again for the great talk.